So we heard 3 talks about different types of tool chains, and each one of them said how great their different compression techniques are. But a key question that the next speaker is going to speak to is about how do we compare them, how do we evaluate, how do we get apples-to-apples comparison of all these things, which is critical for making progress in this field. Otherwise, it's just each one of us kind of promoting our own set of tools. So the next speaker is Vijay Reddi. Vijay is an MLPerf Inference Chair and an Associate Professor in the John Paulson School of Engineering and Applied Sciences at Harvard University. His research interests include compiler architecture and runtime systems, broadly in the context of autonomous machines, mobile, and edge computing systems. Outside of his academic duties and technical research interests, he's heavily involved in the broad outreach of AI for social good. He received a PhD in computer science from Harvard University. And today, Vijay will talk to us about benchmarking ultra-low power machine learning systems. Thank you.
Thank you, Ofer. Thank you, folks, for being here. So today, my talk is going to be rather interesting in that I'm actually going to focus on getting you to solve the problem and laying out what the issue is that's facing us in front of us in terms of understanding the hardware systems and the software systems that we're putting together to do machine learning. Now, I'm going to talk about it specifically in the context of tinyML systems, right? Now, we're all here because we know what tinyML is all about. What you might not be familiar about is what is MLPerf, because my goal at the end of the day is to get you excited about building a tinyMLPerf benchmark suite that will allow you to understand what the performance is of a given piece of platform as compared to another piece of platform in the tinyML space. So I want to build a bridge. So let me start off by first introducing to you what is MLPerf, right? That's the first question. MLPerf is effectively a community-driven benchmark suite, right? It includes many, many different organizations. I bet you many of your own organizations are actually part of MLPerf. What we set out to do a while back, this is almost about a year and a half back or so, our goal is very simple. There's a lot of machine learning hardware that's coming out. In fact, if you look at the news, people would say that there are about 100 different startups just in the ML space, in the ML accelerator space that are out there, right? And the market value is about $60 billion by 2025 or so. This is fantastic. Just one problem. Once you put all this hardware that comes out there, how do you know if you're comparing any two systems in a fair way? For in fact, just today, right, from Qualcomm to ARM to Syntiant to all these great companies, everybody's been talking about what their performance is, what their accuracy degradation is, and so forth. Often the problem with comparing all of these different graphs that we see is that you really have to understand the nuances behind what those numbers are, because there's a lot of different techniques that are going on in terms of optimization. In fact, Harris just talked to us about the different post-quantization related normalization techniques you have, right? There are about 4 or 5 he showed. Those are all totally valid. But if you want to understand what your accuracy degradation is, you need to know what scheme was followed. And so if you don't understand the details, then it's really hard to make sense of the numbers. And so that's the problem that MLPerf really set out to do. It was to create a benchmark suite, effectively pick a set of models, outline a set of clear rules, write out how we actually benchmark any two systems so that we can actually make comparisons between them in a fair way. And that effect is really driven by the community. It is not driven by any one person. It's not driven by me. I simply chair the effort, and I get people together, and I try and get them to understand what we have to do in order to have a systematic benchmark. So what the community has effectively done over the past year and a half is we've built a training benchmark suite. We've done an inference benchmark suite. I'll talk a little bit about this. This is primarily background material, so I can set the stage for what a tinyML benchmark suite needs to look like, right? And sketch out the questions that we need to answer. So with all these companies involved, the goal of MLPerf is to put out benchmarks. The way we do the benchmarking is effectively taking public data sets. Nothing is proprietary. You cannot have some sort of number that's out there that says, well, it's based on some internal data set. So we start with publicly accessible data sets, and we put out training benchmarks, right? And we also put out inference benchmarks. Now, the inference benchmarks are the ones that are quite relevant to this community, because we're not really going to be doing training on our AI chips in tinyML context. And what we specifically do in developing these benchmarks is first and foremost identifying what are the ML tasks that the users really care about. Now, when I say users, I'm not talking about the hardware vendors who want to talk about what their performance is on a given model. What we really care about is what the end user customers want. What do they really want to assess, right? So we want to understand what are those application ML tasks that end users are actually asking for. And from that, we work backwards to defining what are the models that we really have to pick. Because if you think about vision, for instance, in vision, you can have image classification, image segmentation, object detection. There are many, many different tasks, you can do within that particular category. And in that, you want to pick a very specific model. So we go through this exercise of identifying what that needs to be. Then we try and understand how these models are actually exercised. I would argue, coming from an academic perspective, I would argue that the general perception of how ML is actually used in the field is quite naive if you take a step back and look at it. We all kind of think like, okay, it's either throughput-oriented mode or some sort of latency-oriented mode. No. In a practical deployment, by and large, you typically have 4 different scenarios in how models are actually deployed. It's either an offline mode, it's a throughput-oriented mode, or you have a service scenario where you have some sort of Poisson distribution of requests that are coming in at some sort of interval, and that's what's actually getting subject to the model. Or you have something like in a smartphone case where you give it a picture and you effectively just do the inference on one image. Right? So there are these different scenarios that are happening. Take an autonomous car, you might have multiple streams that are concurrently coming. So that's a very specific way of understanding how the model is actually going to perform on a piece of hardware. So we try and capture what these different scenarios are, and that's the second step after you've identified the task. The third is really outlining what the rules are to benchmark. If you want to benchmark the performance on a model, well, you really want to spec out. If you're doing quantization, okay, are you going to allow retraining or are you not allowing retraining, right? Are you doing sparsity optimizations? Do you allow pruning related optimizations? The reason is, if you don't bake those rules down and say, well, you cannot do retraining, well, then you've got a certain trade-off with respect to accuracy. Because once you do quantization, if you don't do retraining, then your accuracy is going to drop. If you do retraining, well, that's great, but you might be doing sparsity and pruning optimizations in the process of doing the retraining, which changes the network structure, which means you end up with actually a different model. So now you're comparing apples and oranges again. Therefore, you have to write out the rules very clearly about what you actually allow in terms of optimizations. Then you got to define the set of metrics you actually want to assess. Some examples of metrics that we tend to look at are like what is latency bounded throughput, for instance, right? Not just throughput, not just latency, it's actually latency bounded throughput. Right? So that's an example of a metric that we try to slice into. And finally, there's a discussion on just how you present results. You would think that's a very, very simple thing to do, but you'd be surprised how much time we spend arguing about how to present a very simple results table on the web page. So this is the general process of actually developing a benchmark suite. MLPerf, we have worked together with the industry, and the industry is the one that's actually come up with this methodology that we have here. There's lots of details behind this. Now, what does it actually get us? If we follow that and we try and do something similar like that for tinyML related devices, then what does it actually enable us to do, right? There's a motivation for us to doing this. First and foremost is just ensuring that we can get reproducible results. When you say you have a certain level of performance on a certain system with a model X, we should be able to reproduce that. In the examples I gave you, if you don't know the nuances of exactly what the software framework did for optimizations, you will not be able to reproduce that. And if you don't control that through the rules, you are going to get very different results, right? So today, just general reproducibility is a pretty big problem in the space. You want to pick representative workloads. What is it that end user customers really want, right? Let's take a simple example. If I'm looking at an autonomous driving, if I use a small little image, 224 by 224, does that really make sense? No, your car is probably going to be bumping into people all the time. Why? Because it cannot see far deep into the image. So you need high-resolution images. That's an example of where you really want to understand what is the use case where the model is being deployed and make sure you capture that into the benchmark suite. And we want to drive innovation. How do you do that? If you don't have a yardstick to measure progress, right? If you can't systematically compare two systems, then when next generation hardware comes out, you don't really know if it's the hardware that's actually better or if it's the software that's actually better. In fact, in MLPerf, for instance, in training we actually showed just from one generation to the next generation, on the exact same piece of hardware, the software got remarkably better in terms of performance. It's only because we could actually systematically measure things that we were able to make that quantification. Taking a step back from a technical sort of standpoint and looking at the bottom set of things, what does this do for us? It enables us to drive the community forward, right? It enables us to have fair and useful measurement. It enables the research community to participate because we're making the results actually reproducible. And one of the key goals is to make benchmarking affordable. This really translates to being able to have academia participate along with the industry folks. Now, here's a sample of what we would envision, right? So this is coming straight out of MLPerf Inference, something that we delivered in October last year. So the first thing we do is kind of identify what are some important areas. Vision and language are two areas that we had identified. Within that, I said there are many different tasks you can perform. You can perform classification, detection, and vision. So we go ahead and get that, right? Because those turned out to be the most dominant uses. Next thing is you got to identify what model is actually representative. Now, there are many nuances about how you pick this. I will get into the details of that as we start thinking about what we need to put together for tinyML. But the idea here is to show you that you have many different models, and no one model is going to solve it all, right? You'd have to pick models that are reflective of what the hardware is actually capable of running effectively. So here, for instance, we pick mobile nets because that's what you end up finding when you're doing image classification on a smartphone versus when you're doing image classification on a bigger system, for instance, like something that you find in an autonomous car. Same thing that goes on the dataset side. We use public datasets. What's really interesting here is the middle row, the MS Coco with 300 by 300 resolution versus 1200 by 1200 resolution. That's specifically pointing out to the example I gave you earlier. If I take a picture with my phone, I tend to use a small resolution. If I'm in a car, I'm using a higher resolution. So the benchmark is effectively trying to capture this extremely vast space. So this is an example of inference. We have training-related examples as well. I'm happy to talk about that offline, but inference is really what we care about here. And then, of course, we present results, right? Everything is made public. The code and everything is open source, so people are able to actually go in and look at the specific implementation for every single result that actually came out. And I'll talk about more about this in a bit. What does this help us really do? If we follow what I just kind of laid out, what does that really get us? What gets us a massive number of actually comparable results. In the first version of this just inference benchmark, we got over 600 unique data points on completely reproducible results. That's spread across over 30 different unique systems. And if you look at the performance range for the benchmark, in terms of what the performance is from the slowest system to the fastest system, that's what the plot is actually showing across all the different benchmark cases that we have. It's about 10,000x difference in performance. So it's kind of capturing what the spread really is in the context of just high-end systems. This data primarily encapsulates everything from like DGX-like systems all the way down to a simple system like a Raspberry Pi. This is effectively what we would like to do for the tinyML space. We want to capture this large breadth of accelerator space and be able to generate plots like this that help us understand what the performance looks like in a very reproducible way. Now, behind the scenes, there's a lot of nuance about what the accuracy thresholds are and what the latency-bounded throughput metrics need to be able to qualify for a result. So we built this. That's great. How does this translate over to this ecosystem here? There are a lot of examples outside where we're seeing that hardware is either coming out or they have hardware demos out there. Right? All of them have models running. What's really interesting, though, right, if you look at all of them, as good as the work is, it's hard for me as someone naively just kind of looking at the presentations to really be able to understand the performance of one system on one table and compare it to the system that's right next to them on the left-hand side. And so what we want to do is build a tinyML benchmark, right? Now, what's interesting about this space? You all know this space far better than we do. But the basic issues really, as compared to a very traditional systems, is that they're extremely resource constrained. Right? Now, the smallest system, the reason I showed you the performance chart on the previous plot was because the smallest system that we got in MLPerf Inference is a Raspberry Pi. That's the smallest one we had. Now, if you just look at the memory consumption of the RAM that you have on a Raspberry Pi, that's about 2 gigabytes, right? Whereas when you compare it to the rest of the microcontroller kind of space, these are in the order of a few hundred kilobytes. Why is that an interesting problem? Well, obviously the models are going to be different, of course, we know that. But what's also interesting is in terms of just being able to benchmark the system, you have a lot of problems. In a traditional large system, you tend to have a system under test, and you have a load generator that's actually generating all of the load that's going in. And we run those things concurrently because the load generator really doesn't demand that much performance from the host. So the system is actually able to do its job almost with negligible overhead. But we cannot assume something like that in this sort of scenario, because any bit of load that you put onto the MCU, you're going to see it. Any bit of load you put onto the accelerator that's coupled with your general purpose processor, your microcontroller, is going to see the difference. So how do we come up with the right methodology is a question for this. What's the benchmarking methodology in just putting load onto a system? and doing that in a way that is actually representative across all kinds of systems that you're going to find. The next thing is often power. When you're benchmarking larger systems, you primarily focus on performance. Power, as much as it is important and everybody acknowledges it, it ends up being secondary in a way. Right? Why? Because it is hard to measure. But you and I know that when we're talking about systems in the tinyML context, right, these are extremely different. Power is a critical first-order constraint. Everybody talks about power. In fact, anyone I was talking to outside was pretty much saying, well, I can get this number at this power, or I can get that number, I can get that other performance number at that power. Power was the key thing that people were emphasizing, right? This becomes a really interesting problem in order to be able to build a benchmark. How do you prioritize power as a first-order criteria and then be able to sort of build an accuracy and performance-related model around it? MLPerf, for instance, has been trying to put together a specification for how you benchmark machine learning systems and their power consumption. But it's actually taken us quite a while, and we still don't have an official spec. But that said, the question here is for people working on the tinyML, like you must be dealing with power measurement on a continuous basis, right? So the question is, how do we sort of incorporate that methodology into a benchmarking setup so that we can get both performance and accuracy together? What are the other challenges that we see? Obviously, we've already sort of seen this in the prior slides where there are many different techniques that people talk about. For quantization, everybody here is talking about quantization. I want to know, what's your quantization scheme, right? Is it symmetric, asymmetric, uniform, stochastic? You don't tell me that, I don't know what you're actually doing underneath the hood. So you can simply say you're doing 8-bit quantization, but my head immediately goes into what are the details of the quantization scheme. Earlier, Ofer was already asking about calibration datasets. If you don't have the calibration dataset, how do you actually capture the range? Right? And I need to know that, because if I don't have that information, the quantization actually doesn't really mean too much, because the second I put it on my data, I'm going to expect a very different result. So that's just one issue with quantization. Then obviously, do you allow sparsity pruning related optimizations where you might change the network structure as a result of that? What are the rules for these for the tinyML systems, right? This is an opportunity to actually declare what those rules need to be. How often or how important are these things? So, well, these are all questions that are interesting. And what we've been trying to do is basically gather a whole bunch of people to try and get them together into a room. And that's honestly why I'm actually here, to try and talk to you about how do we build this benchmark, right? And this is a community-driven effort that we want to do. So a good number of companies have expressed interest in our tinyMLPerf working group in trying to spec out some of the answers to the questions that I was raising earlier. So what are the set of tasks that we want to consider? Just the way we saw about, we looked at things earlier in the inference space. I was saying you have image classification, detection, whatnot. On the left-hand side, we have interesting area categories, right? So here it's less about vision, and it's less about like classification or detection kind of thing in my head. It's much more about what's your sensor kind of stream coming in, right? There's audio, there's image, there's just telemetry that's coming in. So identifying what are those key categories that we have to focus. And then next would be identifying what is a specific use case within each of those categories. And then, of course, there are many different models. One thing that I find interesting about the tinyML space is that it's not purely about machine learning techniques in the non-traditional neural network sense, right? There are many different approaches. You can have a lot of classical machine learning techniques that are just as good or probably even better to actually be deploying on a tinyML system. So we sort of have been talking about what is the right model type that we actually want? Do we necessarily want to have everything that is a neural network, or do we want to have a mixture of neural networks and classical methods in there? And of course, what are the data sets that go with them? So how do we prune that large set down? We have done some effort in this space. The first question is, what is the definition of a benchmark? When you think of a benchmark, it might be something that is going end-to-end use case, where you're looking at pictures coming in from a camera or some sort of sensor, and that's flowing through your DSP, from your DSP into your neural network, and then you get your inference out, and then you do your post-process. Do you look at that end-to-end use case, or do you just look at the neural network processing size? What we end up doing is primarily focusing on the machine learning task alone. And of course, as I showed you in the table earlier, the many different tasks, how do we narrow that space down? The way we try and do it is by talking to customers and trying to get their feedback as to what they think is the most important thing to be able to benchmark. And of course, what is the measure of metric? Here, it seems like power is a first-order constraint for us. How do we sort of factor that in? Implementation equivalence. This is always a really fun one to dabble with, because in any ML system, it's an ML system. It's not an ML device. It's not an ML piece of hardware. An accelerator is always tightly coupled with the software. We've heard this many times today, right? So how do we sort of benchmark that? Well, the problem is, even if you specify a model, almost everybody's going to take that model and they're going to have to effectively re-implement it. So you get into this issue of model equivalence because they're going to have to modify the model and implementation somehow in order to map it onto their hardware effectively. So how do you define the equivalence-related rules? And another issue is, as we talked about earlier, things about quantization and retraining. Do you allow them? Do you not allow them? And so forth. And finally, do you normalize the results or not? Bullet number 6 alone we could have a long debate about. So just a bit of rationale, before I show you like what are the small sets that we have come down to. Think about maturity. There's a certain set of guidelines we want to have, right? How mature is the problem space? Do you take the most advanced model that just literally came out that everybody's talking about, but the industry has not quite yet put this into the production pipelines? Or do you take something that's actually been used right now, like ResNet 50 is still a good model, or do you have something like AlexNet that dates way back, right? So you want to have some sort of principle, and the idea is to pick something that's cutting edge where the industry does have a bit of experience, but not something that's too far out. Variety, you have different types of networks. This was the middle column that I was showing you. RNNs, CNNs, decision trees, boosters, right? So there are many different methods. So you want to have a balance of that so your benchmark is actually representative. And the complexity, the hardware complexity that's actually needed, right? Do you pick something that is extremely hard for people to optimize or not? And practicality. Do you actually have data sets that are available for something? Like you might want this ideal benchmark, but the principle that we follow is anything that you can get out of the door quick is much better than trying to wait for something that is ideal that will never actually land. So the starting place where the group is at this point is this is just a straw man person. We haven't quite baked it in. I'm just showing you this so you can give us the feedback and come and participate and say, no, this is the wrong data set. No, this is the wrong model or the wrong task you're focusing on. So the primary area has been like picking 3 different task categories, right? One in audio, visual, and behavioral, and picking well-known use case scenarios in this thing, and going off of public data sets, as I mentioned earlier. If you want to find out details, Kobe actually, who's been running the working group, has a fair bit of details on this. But generally what we have done is we've gotten to the point where following the methodologies that MLPerf has done very well on in the past, we're trying to understand how to map them for the tinyML hardware that we expect to be seeing quite heavily in the next year to 2 years or so. And effectively identifying methodologies that we need to have. What we often find in the tinyML context when we talk to people is that you cannot directly adopt the methodology that you have for large cloud and edge scale computing systems or even mobile scale computing systems. It seems like the tinyML space actually, if you want to benchmark them, people often do very tight coupling of algorithm and hardware co-design because it is usually one kind of specific use case that your device is kind of targeting, right? And so it actually really presents a new challenge in terms of understanding how we do benchmarking. And so we've been thinking about this as a group. So the point I'm trying to say is benchmarking systems is really hard. MLPerf has made a pass at this. We know quite a lot about how to build benchmarks for ML systems, but I think tinyML presents a very particular set of challenges that no one has kind of seen before. And the communities are vastly different. Right? So point is, we would love it if you could actually come and engage with us and help us actually build a benchmark that you want to run your systems on and get data from which you can actually understand what the systems are doing. If you are curious about the methodologies and principles we do, we have these white papers you're welcome to read. And with that, I'm happy to take any questions if you have. Thank you.